Hello, I welcome you all to this another interesting screencast, and the problem reads the V belt has an inner radius of 6 inches and the cross-sectional area is shown. Determine the outside surface area of the belt, and the follow-up question reads a V belt has an inner radius of 6 inches and a cross-sectional area is shown. Determine the volume of the material used in the material used in making the V belt. So both these particular problems are coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. So let's briefly talk about what V-belt is. So we have the V-belt that I've shown in this particular image. And we have also different cross sections. They come in a variety of different types. Okay. So we have been told that the inner radius for this V belt, so imagine this is the center here. So the inner radius up to there, okay, is 6 inches. All right. So these are the V belts. These are the different cross sections. Okay, they come in different varieties. So what is a V belt? Basically, a V belt is a flexible and efficient power transmission device capable of transferring power from one shaft to another. It is known for its trapezoidal shape that wedges securely into the sheaves of a shaft. So the unique shape of V-belts help them fit tightly and snugly into the grooves of the sheave, giving them additional surface contact and increased stability. Belt drives transmit power between two or more rotating shafts, usually with parallel axes of rotation. The belts are looped over pulleys attached to the driver and the follower shafts. The pulleys are placed at a measured distance to create tension on the belt, and the friction causes the belt to grip the pulley when in operation. So basically, this is what a V-belt is. So you can just think of a V-belt as a device that transmits mechanical power, okay, in a machine. Okay, so it transmits mechanical power from one component to the other of a given machine. Right. So let's go to the problem. Let's go to the problem. Let me just get rid of this. So in this particular problem, we have been asked to solve. We have been asked to solve the surface area, to determine the surface area as well as the volume. So we are going to use two concepts that were developed by two individuals by the name of Papas and Gidnas. Okay, so the two developed theorems. All right, and the theorem says the surface area, okay, of any given line or curve is equal to the angle of revolution theta, which is expressed in radians, times the centroid or perpendicular. This is the centroid distance, and this distance is measured perpendicular to the axis of rotation. Okay, this is centroid distance measured perpendicular to the centroid, to the axis of rotation. And then we have the length of that particular curve. So if you have a curve like this, and let's say this is your axis of rotation, then we are going to say this distance here, this one here, this distance here Okay. Okay. All right. So let's say we have this distance here. This distance here is our centroid or distance perpendicular to the axis. So this is the axis of rotation. All right. So, and this is our curve. Okay. So, and this curve has a certain length. All right. This curve has a certain length L. All right. So, this is how they defined the surface area, purpose and goodness. And then they also went further to define the volume, where they said volume itself also is equal to the angle of revolution, and is expressed in radians, times the centroid or distance of an area that is being revolved, then times the area. So again, it can be any shape. Imagine this is a shape that we are dealing with of this area. Okay, and then this is the axis of rotation. Okay, this is the axis of rotation. So let's say this distance here is our centroid or distance perpendicular to the axis of rotation, and this is our area. All right. So if we are to revolve this about this particular axis of whatever given angle, then we are able to compute the volume. So these are the two equations that we are going to use. All right. So what is important in this particular question is to understand the problem and exactly what they are talking about, because chances of making mistakes are there. All right. So we have been told, we've seen how the belt looks. So our axis of rotation is going to be at this point. Let's say at this point here. This is our axis of rotation. Let me make it a little bit bold. Here. So this is our axis of rotation. Of course, we are first defining the first case, which is 9-99. So this axis of rotation, right? All right. So now let's define the lines. So this time around, we have lines that we want to use to compute the area, the surface area, this surface area, this surface area. Seeing this one for the whole belt, which is 360 degrees. Okay, so that is what we want to look at. So how many lines do we have? Let's define them. So we have these lines. Let me start with the bottom one. This one here. Okay, and then we have these two, this and this, and then later on we have this. Okay, so let's label them. So let's call this one as our line 1. Okay, we call this one as let me just wrap this. All right, so let's call this as line 1. Then these okay, all right, so this one as our line 1. Okay, sorry, this is our line 1 here. Then this one, the green one is 2. There are 2. The green ones, they are the same, because this particular cross section is symmetrical about the vertical axis, this axis. Okay, and then we have line 3. All right, great. So now let's define our distances from the axis of rotation. So being told the inner radius has 6 inches radius. Okay, 6 inches, and then at the same point, we are going to have at this particular point, let's say somewhere here, somewhere there, we'll have, okay, there we'll have centroid distance. Let me cut it like so there, so that I just make it in two. And then I'll have another one, centroid distance there, like so. Okay, I cut them in two also. Alright, so there we go. There we go. Great. So let's label this. So we have the first one here, which is 6 inch. This is 6 inch. This one is 6 inch. Of course, this is also 6 inch, and this is 6 inch. Okay. Then the centroid distance for this line number 2. Okay, line number 2 is just going to be equal to half the length of this particular height. So we don't have this height, so we can calculate it. Let's calculate it. We have the angle there. We have the angle, so this distance here from there to there, let's calculate that. So we can write it down here. So if the whole angle is 30, therefore we expect this angle here to be equal to half of 30, right? Not so. This is going to be equal to what? This is going to be equal to 15. This is 15. Alright. So if this is 15, then we expect this to be equal to, so we have something like this. This is 15. And then this one here is 0.25. Okay, and then we want this that we're going to call h. So we know that tan 15 is just going to be equal to 0.25 divided by h, and therefore h is just equal to 0.25 divided by tan 15. So this one is 0.25 divided by tan 15. Okay, so this length here is just equal to this one here is just going to be equal to 0.25 divided by 2 tan 15 half. Okay, understand? There is no space here, we write it inside. So this is just going to be equal to 0.25 divided by, of course, half tan 15. So this is this distance here. That is the centroid or distance perpendicular to the axis of rotation. It's just half the length, the height for a line. Okay. Then the centroid or distance for line 3, it is just the whole height itself is just 0.25 divided by tan 15. Then the centroid distance for line 1 is just 6 inches. Before we draw the table, let's write down some of the information we need. So length for line 1 is 0.5. Length for line 2 is 2 by 0.25 divided by tan 15, which is just equal to 0.5 divided by tan 15. Then line 3, the each length is a 1. Okay, a 1 inch. Alright, and then what else? Sorry. So before we draw the table, we need to find the lengths of these particular lines. So the length for line 1 is just equal to 0.5. For line 2, we have something like this. Okay, and this is 0.5. Alright, so this, we're going to have a sine 15. Imagine this is our hypotenuse. Sine 15 is equal to 0.25 divided by hypotenuse. Then the hypotenuse is just equal to 0.25 divided by sine 15. So therefore, the length for line 2 is just point, and there are 2 of them. So multiply by 2. So it is 2 by 0.25 divided by sine 15. Okay, and this is just going to be equal to 0.5 divided by sine 15. Line 3 is just equal to 1 inch. Alright, what else? And then R curved 1 is just equal to 6 inches. These are all inches. Okay. Then R curved 2 is just equal to 6 inch plus 0.25 divided by 2 tan 15, right? And R curved 3 just equal to 6 plus 0.25 divided by tan 15. So we have all the information that we can feed. We are using this formula, theta summation of R curved L. Alright, so let's write a table here. So we have part. So we have part 1. Theta, of course, is 360. In radians is 2 pi. R curved 1 said is 6 inches. Of course, this is in inches, and this is also in inches, and this one is inches squared. Okay, then L, the length is L1, L1 is the length, okay, L1, the length is 0.5, and then the product of that is just 6 pi. And part number 2, of course, 2 pi is in all cases. For the centroid or perpendicular centroid or distance, we say the 6 plus 0.25 divided by 2 tan 15. Okay, this length is 2, there are 2 of them, 0.5 divided by sine 15. Okay, so if we were to work out that, do the multiplication, then we'll have a 3 divided by sine, a 3 divided by sine 15. Can I work it out in advance? I think I can. Let me just multiply it so that it will be able to fit. So I have a 6 plus, okay, 0.25 divided by 2 tan 15 plus 6 times 0.5 divided by sine 15, then times 2. Okay, so this gives us a 24.9847 pi. I repeat this, 1.25 divided by 2, 25 divided by 2 tan 15 plus 6 times 0.5 divided by sine 15, then times 2. Alright, so that is fine. And then the third case, the centroid or distance is a 6 plus 0.25 tan 15, and then the length is 1. When we do the multiplication, we have 0.25 divided by tan 15, okay, plus 6 by 2. So this gives us a 13.8660 pi. Okay, so 0.25 divided by tan 15 plus 6 times 2. Great, let's sum them up. So this plus 24.9847 plus 6, everything times pi. So we have a 114. We have a 140.90. Okay. So the area, therefore, the surface area is equal to 140.90 inches squared. So let's go to the second case. So let's draw this once more again. This is equal to 0.25 divided by tan 15. This is 0.5. This is 0.5. This is 0.25. And so is this. Great. So what is, for the first one, this one is just going to be equal to half this height, 2.5 divided by 2 tan 15 degrees. Sorry, it's not, I meant for the rectangle, area 1. Sorry, so I meant this one, 2.5, 0.24.5, half of this. Okay. Hold on. Tan 15 like so. Okay. Then this one is going to be equal to 2/3. It's 2/3 of 0.25 divided by tan 15, which is equal to 0.5 divided by 3 tan 15 degrees. Okay, so let's define area 1. Area 1 is just going to be equal to half times the base, 0.25, times the height, which is 0.25 divided by tan 15. Therefore, area 1 is just going to be equal to that's 0.25 and divided by 2. This just becomes a 0.03125 divided by tan. This is area 2, sorry. Area 1 is just going to be equal to 0.5 times the height, which is 0.25 divided by tan 15. Therefore, this is just going to be equal to 0.25 divided by 2 tan 15. Area 2, there are 2 of them, so it's 2 times half times 0.25 times 0.25 times another 0.25 divided by tan 15. Therefore, this just becomes equal to 0.25 squared divided by tan 15. Alright. What else? Then we have got these distances, which is L arcade 1. Arcade 1. Let me create a boundary. We have a boundary, something like this, something like this, something like this. Okay. So R1 for this, for the first area, is just going to be equal to 6. Is equal to 6 plus 0.25 divided by 2 tan 15. Area 2 is just going to be equal to 6 plus 6 plus 0.5 divided by 3 tan 15. Okay, so we have everything. Let's draw up a table. So I will start also here. I have part. Mind you, we are using this equation. We are finding volume in the second case. So this one was case number 1. I need to indicate here. This one was case 9-99. Okay. And then we'll start the other case here, which is case 9-110. Alright, like so. So we are using the formula. Volume is equal to theta times summation of the perpendicular centroid distance times area. Okay, so there we go. So we have part, right? Great. Let's fit. So for part 1, theta of course is 2 pi, and then we have R1. Said R1 is just a 6 plus 0.25 divided by 2 tan 15. Area we said is a 0.25. Is a 0.25, right? So we said area is just the base times the height. The base times the height, which is just 0.25 divided by 2 tan 15. Then when we do the multiplication, let's do it. So we have 0.25 divided by 2 tan 15 plus 6 times 0.25 divided by 2 tan 15 times 2. So this gives us a 6.0333 pi. Okay, so 0.25 divided by 2 tan 15 plus 6 by 0.25 divided by 2 tan 15 by 2. Okay, then in the second case, of course, 2 pi, and then R2 is a 6 plus 0.5 divided by 3 tan 15. Then area for 2 areas, so it's 0.25 squared, 0.2 squared divided by tan 15. So let's work it out. 0.5 divided by 3 tan 15, okay, plus 6 times 0.5 squared divided by tan 15 by 2. So this gives us a 3.0892 pi. I repeat it, 0.5 divided by 3 tan 15 plus 6 times 0.25 squared divided by tan 15 by 2. 3.0892. So plus 6.0333 times pi. Okay, so we have a 28.66. So volume therefore is just going to be equal to 28.66 inches cubed. Alright, so I think we are done. We have the first solution there, which is the surface area, and then we have the volume, Right. I think this is about it. I hope the video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and sharing my channel. Bye bye. See you in my next screencast.